Alright, let's pick it up and let's get into some trig functions now. So we're going to do some basic integrals for some trig functions. So if we take a look at example 17, we have the integral of sine of x divided by cosine squared of x. Once again, that's a good idea to potentially break this into two different trig functions that are multiplied together. So with these, you might want to have the inside book cover sheets out so that you can kind of see your vision of where you're going to take these trig functions so they can get to one that you can take the antiderivative of. So in this case, we got a cosine squared. If we had something else in the numerator that looked like we might want to use the Pythagorean formula for trig, we'll get to one of those a little later on, then we'd want to apply this. But for this one, let's separate it into 1 over cosine of x times sine of x over cosine of x. Okay, what does that give us? Well, we can rewrite 1 over cosine of x, okay, so that it's in a little bit better form for us. So we will use that as secant of x, and then sine of x over cosine of x turns into tangent of x. So we have secant x, tangent x, dx. So that's our integral. If we look at those sheets that are from the inside cover of our trig book, or not our trig book, our calculus book that I have for you guys, it shows right on there this exact integral becomes secant of x plus c. Now, if we're good at working the other way, right, the derivative of secant x is what? Secant x tangent x. So being able to check yourself and go that direction. Let's look at example 18 now. We have the integral of 5 cosine of x plus 4 sine of x dx. We could break that into two integrals if we want, or keep that constant in front with the trig functions. Alright, and we take the antiderivative of cosine, which is sine, okay, and then the antiderivative of sine is minus cosine here. Because we got to remember, it's a little tricky when we work backwards with cosine. Remember, the derivative of cosine is minus the sine, which would make this a plus, right? Because we'd have minus sine and then this minus. That's how we'd get that plus sine back. The derivative of sine is cosine. Alright, so just always double check when you're going back and forth between sine and cosine, keeping track of the sign and which one needs to be negative. Alright, and don't forget the plus c. Now, this one, we have the integral of secant squared theta minus sine of theta d theta. Once again, I've made notes on here. Okay, you can look back at our integral table that I wrote down on page 4, or the inside notes from your book cover, that 4 pages that I gave you guys there. So we can see that these are already kind of perfect antiderivatives of each other. So the antiderivative of secant squared theta is tangent of theta, and the antiderivative of negative sine theta is a positive cosine theta. So we can rewrite this integral as tangent of theta plus cosine of theta plus c. Once again, just anytime we got sine cosine involved, or cosecant or cotangent, please make sure that we are always being aware of the negative sign and when we need to use it and when we need to apply it. But once again, make sure that you have those inside covers of the book handout with you. It'll really make it easy for you. Or I wrote most of them down a few pages earlier in the notes, but definitely have those on there. Looking for those perfect integrals where we don't have to do a lot of work or algebra manipulation to get through them. So like this scenario, okay, a little bit of algebra. We're looking at example 20 here. We have the integral of secant of y times the quantity of tangent of y minus secant of y dy. So sometimes it works to distribute through because it makes it a little bit more complicated. Sometimes it doesn't. Sometimes you might just have to kind of try on these scenarios. So let's go ahead and distribute that secant of y through. So when we distribute secant of y, we're going to distribute it to each term here, to the tangent term and to the secant term. So when we do that, okay, we're going to get secant y tangent of y minus secant squared of y. Now we got perfect integrals here. We have secant y tangent y. We did that one a little bit earlier. We know that the antiderivative of secant y tangent y is secant y. Then we know that the antiderivative of secant squared y is tangent of y. Once again, that comes from our integral table and the inside covers of the book. Later on, we'll kind of figure out how to get there with some different methods. Alright, but we can double check this by taking the derivative here. The derivative of secant y is secant tangent. The derivative of tangent is secant squared. So just check yourself, okay? Some of the homework problems you might get stuck. Maybe use some of the answer choices and take the derivative and see if you get the integral. See if that's something that can kind of help you out there. So this one ends up being secant y minus tangent y plus some sort of constant of integration. Okay. Next time we're going to start applying initial conditions where we can actually solve for what that constant of integration c is going to be.